Hi, I'm MarcDavisMarsh. I'm an applications engineer here at Texas Instruments. Today we're going to be looking at how to make your thermal design simple. We're going to be looking at the LM43603, which is part of a new synchronous family of simple switcher regulators. So why does thermal performance matter? I think we can take a look at this next slide and you'll really understand. So if we look at that slide, it's pretty simple to see that as the temperature rises, you're more likely to have failures. And failures are things that we definitely don't want to see in the electronics industry. What are the other advantages of thermal performance? Let's take a look. We're talking power capability. Higher currents, more processors, you're going to be able to do more when you can process with more power. You're also going to be able to run at higher ambient temperatures because your devices won't be as hot. So all of that's going to improve the performance besides just the reliability. So how do we know how hot everything is? We're going to estimate the junction temperature of a die. It's a very simple equation. It's just the junction temperature is equal to the IC rise temperature, which is equal to the power dissipation in the IC, multiplied by the theta JA, which is the thermal impedance from the junction to the ambient, and you add that to your ambient temperature. Now, getting those values seems complicated, but we've made it simple. The power dissipation can be taken from the data sheet, and the theta JA, we also have curves in the data sheet. And if that's not simple enough, we also have the ability to get these values in WebBench. So the new Simple Switcher synchronous family has 36 volt and 60 volt rated parts, and all of those parts are going to apply to what I'm showing you here for the LM43603. So all of the thermal performance that I'm showing here, you can also see on this family of parts. Let's do an example. So here I'm showing an example of the efficiency curve taken from the data sheet. You then back calculate the power dissipation, and then you take the theta JA curve from page 40 of the data sheet, and that's going to allow you to easily estimate the theta JA value and multiply it by the power dissipation, giving you the junction temperature that you need to design with. Now, the LM43603 is optimized for thermal layout. It's got a large exposed pad, which you can easily route the copper to away from the part. That will allow the heat to spread away from the part. It also, that large exposed pad allows you to put thermal vias down to other layers. Those layers, such as a ground layer, could then spread the heat away from the part. It also has the power ground pins immediately adjacent to the exposed pad. You can then have a large copper area that's unbroken. Unbroken copper is your friend. It's going to get the heat away from the part. It's going to spread it out, and you're going to end up with a great thermal design. So what we need to do now is, you've seen why the layout is good for thermal design. Let's see how that looks in real life and also on WebBench. So I'm going to design using WebBench, and then we're going to compare that to a thermal camera here in the lab. So if we go to the product page for the LM43603 and we scroll down to the WebBench section, I'm going to put in 12 volts to 3.3 volts out at 3 amps. Ambient temperature in the lab today is around 25, and I'm going to open the new design. Now, this design is optimized for cost and efficiency, but it doesn't match the thermal camera design. So I'm going to change the frequency to match the board we have on the thermal camera at 500 kilohertz. Now you can see that the WebBench design has efficiency, a schematic, a bill of materials, and operating values. In the operating values, we have the IC power dissipation, and you can use this in your equation for junction temperature. But we can do one better than that. If we go to the thermal tab, we can actually run a thermal simulation. The thermal simulation is going to be very precise, and it's going to let you see how the heat's going to spread across the evaluation board. So let's set it to 12 volts in, 3 amps out. We'll set the ambient temperature to 25 and the copper weight of the board to 2 ounces and run a simulation. And while that's running, let me show you the thermal camera design. So what we have here is a thermal camera. We have the evaluation board in this box. Now the reason it's in the box is so that we can keep the ambient air flow from moving. So if we restrict the airflow, then it's going to match the simulation better. Now what you see on the screen here is we have the IC. This is actually the inductor. And then in this region here, we're measuring the max temperature. And you can see that it is around 57, 58 degrees C. So let's see how that compares to WebBench. So this is a simulation from WebTherm. Now I'm going to adjust it so we can get some color variation. And then zoom in so we can see the board a little better. So here we can see the IC. Again, here's the inductor. And if we look up here at the top, you can see that WebTherm is estimating a max junction temperature of 59 degrees C. So we can compare that to our thermal camera, and we can see that they're only a couple degrees off. And then we realize also there's going to be some variation. The camera is actually measuring the top case temperature, not the junction temperature. So the junction temperature will actually be a few degrees higher. And WebTherm is actually estimating junction temperature here. So in summary, the LM43603 is really designed for an easy thermal layout with its large exposed pad and its pinout. And we have the tools in the datasheet and in WebBench for you to do a very simple thermal design. If you have any more questions, go to SimpleSwitcher.com. Thank you for watching.